Hello and welcome to The Daily Space. I'm your host, Dr. Pamela Gay, and I am here by myself to put science in your brain while Beth takes a well deserved day off. Yesterday, a short little letter for physics letters B was published that was filled with equations and broke my brain with science. Researchers Xavier Calmet and Volkert Kuipers have a new work accepted into the journal Physics Letters B, and in it they work out new limits on the mass of individual particles of dark matter. As the name implies, dark matter is stuff that doesn't interact or emit light. It makes up about 27% of the universe, and because it is only seen to interact via gravity, it is super hard to understand. According to Kelmet, this is the first time that anyone has thought to use what we know about quantum gravity as a way to calculate the mass range for dark matter. We were surprised when we realized no one had done this before, as were fellow scientists reviewing our paper. What we've done shows that dark matter cannot be either ultralight or super heavy, as some theorize, unless there is an as yet unknown additional force acting on it. This piece of research helps physicists in two ways. It focuses the search area for dark matter, and it will potentially also help reveal whether or not there is a mysterious unknown additional force in the universe. End quote. The limits they derived put the mass energy of any one dark matter particle between 10 to the minus 3 electron volts and 10 to the 7 electron volts. To put this in context with other particles, they find dark matter should have masses in the range similar to neutrinos or electrons. This consistency with neutrino masses is particularly tantalizing to me. While not discussed in this paper, many researchers have wondered if the annoyingly difficult to observe neutrino could be related to or a form of dark matter. This work doesn't rule out that possibility. To get at these limits, Calmet and Kuipers considered factors such as how fast would particles of different sizes decay, how big must it be to not require additional forces, and even what limits are created by that Pauli exclusion principle that so many of us learned in high school chemistry. While this is a very elegant paper, it does have limits. At the most simplistic limit level, there could be physics at play that we don't know about, and some of the assumptions that they made, such as quantum gravity following the traditional Planck scale, those are assumptions, and they could be wrong. But this is a first step. And this first step seems to confirm that dark matter can be explained with known physics as a particle of reasonable size that we just may be following the right path toward discovering. While some physicists look to define dark matter with theoretical physics, others are out there trying to understand it from how it moves luminous matter. Dark matter is pretty much everywhere in our universe, but it has its highest densities in galaxy clusters. This has been determined by looking at how the gravitational pulls of dark matter twists the light of background objects. While this technique, called weak lensing, can get us good information on the distribution of dark matter, it doesn't give us a very detailed image. Coming to the rescue is intra-cluster light, light from stars that have been torn from galaxies and now live in the spaces between galaxies. This light is extremely faint and requires near Herculean observing efforts to see. Well, the Dark Energy Survey, with its sensitive camera and long observations, has taken on this task and found gold, or at least intra-cluster light. Researcher Yanyan Zhang explains, observationally, we discovered that intracluster light is a pretty good radial tracer of dark matter. That means that where intracluster light is relatively bright, the dark matter is relatively dense. These results were checked against weak gravitational lensing results, and everything matched. This work combines data from 500 different clusters within 3.3 billion light years and helps us understand how dark matter is distributed in our modern universe. Seeing intracluster light in more distant galaxies is a goal for this team. Since the light from distant clusters has been traveling for longer, we can essentially look back in time by looking at farther away systems. In this case, distant clusters could allow us to understand how the distribution of dark matter has changed over time. Zhang goes on to say, "My dream is to go all the way to 10 billion light years. Studies say that's when the intercluster light has just started to evolve." End quote. Getting the dreamed of data won't be easy, but we don't do science because it's easy. We wish Zhang and her team all the clear skies. After the break, we're going to bring things back down to Earth and look at how Germany was once hit by 2 asteroids in the very distant past. In a previous episode, we talked about how geologists use global navigation satellite systems to measure changes in the surface of the Earth, especially in areas that have regular earthquakes. There is an entire system called the Network of the Americas, NODA, that has GPS and GNSS stations all along the west coast of the United States and down to the Caribbean. And the data taken from these stations is collected continuously. This process allows scientists to understand the interactions between various plate boundaries, such as the San Andreas Fault in California. Now scientists have taken all that data collected between 2007 and 2019 in much of California and compared the results to meteorological data from the same time period. The question the team was seeking to answer was if long-term weather pattern changes, such as the multi-year drought from 2012 to 2015, had an effect on the amount of deformation the region experienced. And the short answer was yes. Prior to this study, published in JGR Solid Earth, scientists had come to understand that short-term seasonal changes in the weather had an effect on crustal deformation and even impacted local earthquakes. Basically, the ground compacts during wet winter months, like now, and rebounds during the drier summer months. So what happens when the area doesn't get much rain for 3 years? The usual rebound or dilation of the crust was half what it was in normal wet years. Apparently, you can't get a pull without much of a push first. More research is needed to understand just how these long-term variations in the weather actually affect the earthquake history in the region. We'll keep you informed of any new developments. Earthquakes are just one of the ways the universe is trying to kill us, and it's a relatively tame method compared to the universe sending rocks at the surface of the planet. Just one big rock, and bye-bye dinosaurs. Then you take a look at the surface of the moon and think, that's a lot of craters. Good thing Earth doesn't look like that, except that it kind of does. And we hide it really well with vegetation and erosion. Still, it's a bit shocking to find 2 large craters close to one another here on Earth. And for a long time, scientists thought that these double craters were the result of binary asteroids, 2 asteroids orbiting each other that hit the Earth at about the same time. That hypothesis was disproved because binary asteroids orbit each other too closely to leave separate craters. They would have to enter our atmosphere separately. And that's not a likely scenario. Now, in recent research published in the journal Scientific Reports, a team led by Elmar Buchner has analyzed 2 craters in Germany to understand their provenance. One of the 2 is the 24-kilometer Rise crater that encompasses the town of Nordlingen, and the other is the 4-kilometer Steinheim Basin, about 40 kilometers away. The team found that the Rise crater is about 11.8 million years old, and the basin is thought to be about the same. Plus, the rocks in the area show evidence of two separate seismic events, which means that the region got a 1-2 punch of asteroid strikes, maybe a couple 100,000 years apart. Planetary scientist William Botke, who has studied double craters but wasn't involved in this particular research, noted, if you only have so much terrain and you keep adding craters, eventually two are going to be very close to one another, just by chance. Sorry, Germany. After the break, we will pause to remember the brave astronauts who gave their lives to advance our trek in space. We talk a lot on the Daily Space about how space is hard. It's a mantra of sorts when it comes to failed rocket launches and test flights. Unfortunately, we've lost people to the cause of advancing space science and engineering. Today is NASA's Day of Remembrance, and we honor the sacrifices and memories of those who gave their lives in the Apollo 1, Challenger, and Columbia missions. For me personally, the Challenger mission came in 6th grade, and growing up in New England, it seemed all my teachers knew Krista McAuliffe. And then Columbia came my first year as a journalist, and having to drive into work on a weekend to write that story. That was the first breaking news I covered. This is a hard day for many of us who have our heart in space. First, we honor Gus Grissom, Ed White, and Roger Chaffee, the Apollo 1 astronauts lost when a fire broke out in the Apollo capsule during a pre-launch test on January 27, 1967. The sacrifice these astronauts made led to a redesign of how capsules are made, changing both the atmospheric composition to make it less flammable, and changing how the hatches work to make sure that astronauts on their own could always open the door out. Next, we honor the crew of the Space Shuttle Challenger, which broke apart 73 seconds after launch on January 28, 1986, 35 years ago today. Those astronauts were mission specialist Ellison Onzuka, pilot Michael Smith, payload specialist Krista McAuliffe, Commander Dick Scobie, payload specialist Grigory Javis, mission specialist Judith Resnick, and mission specialist Ronald McNair. This mission was lost due to an O-ring failure. The investigation that followed made it clear that we need to have more ready communications across all levels of mission preparation. We learned from the people that we lost so that we can better keep people safe in the future by paying attention to even the lowest people in the totem pole, because sometimes they're the ones that know what's needed to keep people safe. Finally, we honor the crew of the Space Shuttle Columbia, who were lost on February 1st, 2003, when the shuttle broke up upon re-entry. Those astronauts were Mission Specialist David Brown, Commander Rick Husband, Mission Specialist Laura Blair Sultan Clark, Mission Specialist Kalpana Chawla, Payload Commander Michael Anderson, Pilot William McCool, and Payload Specialist Ilham Ramon. Their mission broke up after, on takeoff, a piece of foam from the external tank struck the left wing and damaged its heat shields. While it was suspected something could have happened, the decision was made not to have the astronauts go and check because no one thought they could actually do something to try and rescue the spacecraft if they had to. During landing, the mission broke up over Texas. And it's the kind of thing that forced NASA to change how it works so that astronauts did have the ability to check out what was going on with their spacecraft, to make sure they were okay, and in some cases have the ability to make repairs so they could come home safe. Space is hard, and astronauts know they could die. They are a new kind of test pilot, and it is on us to never take them for granted or stop striving to over-engineer towards success. Their sacrifices led to improvements in spacecraft design and procedures for protecting future crews. As NASA's acting administrator, Steve Juzik, writes, "As we work to achieve our goals of putting the first woman and next man on the moon and send the first humans to Mars, let us pause for a moment to remember." Exploring space is hard, but that sky above and all the stars and worlds within it, those are something shared by all mankind. And you can go out if your skies are clear and look at the same stars that someone literally half a world away may be looking at the same time, assuming you're looking close to the horizon. You can only share the sky with half a world at the time. The brightest object in the night sky right now is the moon, and tonight it's full. This particular full moon has several names: the wolf moon, the snow moon, or the hunger moon. All these names evoke feelings of deep winter and isolation here in the Northern Hemisphere. Well, okay, we get snow moon and hunger moon, but why wolf moon? Where does that name come from? Are we thinking of a lone wolf howling in the winter night, or a pack of wolves hunting outside a hungry, cold village? There's an easy tendency to think that it's a Native American name, but that actually isn't the case. According to an article in Indian Country Today, the closest known Native American name for this full moon is Wolves Run Together Moon by the Sioux. Other tribes have different names, of course, and we're not going to attempt the native versions out of respect for the beauty of their languages. So here are some translated names. The Algonquin call this moon "sun has not strength to thaw." In Alaska, the Haida call it "bear hunting moon." In southwest Arizona, the Hopi call it "moon of life at its height." In the Pacific Northwest, the name is "stay inside." I particularly agree with that particular one. And the Choctaw in the south call this moon "winter's little brother." What's your favorite name? Personally, I like "moon of life at its height." I feel almost energized hearing that name. I suspect there is some influence of cold desert nights and pleasant winter days on that name. Although "stay inside" is good too. Simple, succinct, and honest. Between the rain in California and the snow here in Illinois, and just about everywhere else, staying inside sounds like a good idea. Whatever you call it, make sure you take a look at it, and may it bring you joy during these long winter nights. Or if you're in the Southern Hemisphere, may it bring you joy on these hot summer nights. That moon that is so very beautiful also makes seeing anything faint in the sky nearly impossible. And the best things in the sky right now are faint galaxies. One of the things we just don't think about a lot is how we live inside a massive disk of stars. And as our planet swings around the sun, the part of that disk that we see changes. Right now, we're looking away from the galaxy's center. The band of the Milky Way that passes near Orion as it spills across the sky is thinner and fainter than when we're looking toward the Milky Way's center in the summer. For folks like me who have done work observing galaxies, now is the time of year to spend at an observatory. We just have a much clearer view out of our galaxy to all the galaxies out there. Basically, while all the bright things we see with our eyes, for the most part, are stars, with a telescope, everywhere you look above and below that Milky Way's white spill across the sky, everywhere you look is filled with galaxies, outlined here in orange and red in the image that we're showing you. The Andromeda Galaxy is one of those many galaxies out there right now, shining just bright enough to be seen with your eyes, except there's a moon. There's a moon. You probably can't see it because of that moon we have right now. If you still want to try and see Andromeda with your eyes, one of the best tools to help is an app for your phone like Sky Safari that can use the GPS and sensors to figure out what part of the sky is located behind your phone. There's a lot of different software that can do this, but I have a soft spot for Sky Safari because it's not only easy to use, but the company behind Sky Safari has donated back proceeds from their sales to astronomy education many different times over the years. If you have clear skies now, get used to using the software to understand how to find bright objects like Mars. And then, when that pesky moon goes away, you'll be ready to find amazing dark sky objects like the Andromeda Galaxy. For now, though, we have a moon. As a side note, we are recording this episode at 1 p.m. Eastern, and at this time, SpaceX looks like they're going to be doing something with their Starship SN9. It looks like they're probably not going to be doing a launch test, but that could change between when we record this and when it airs. We want to remind everyone, space is hard, and it is amazing to see what humans are capable of. Even when we fail, we keep going, and we keep trying to accomplish more and more. Thanks for watching. This has been The Daily Space.